Now, although finding limits graphically is a great way to find limits, sometimes if you're not given the graph, to actually do the graph yourself would take quite a bit of time, especially if it's a complex graph. So it's also important to be able to find limits algebraically if the function is given to you, but not the graph. In the example that we did previously in part one, of course, if it's a line, you can always, graph a line easy, but it could be much more complex than that. So here we have three very important, I should say four very important limits that will be true, and I will explain kind of why they are true. So you have the limits of a linear function, a line, polynomial, and rational functions. So the first one is for any constant k, the limit as x approaches c of k is k. Now remember that if you have a constant k, that means that your graph is a horizontal line, right? So if we graph a horizontal line up here, any x you pick, any x, the limit from the left of that x and the limit from the right of that x would still be, for example, if I pick here, so if I pick from this side, say this is the x I'm looking at, and then from this side, the y is still going to just be k, right? If this is y equals k. So no matter which x you are approaching, from the left and from the right, the y is still going to be k. So if you have a constant k, the limit to any x is k. Now we have the limit as x approaches c of x is equal to c. Now again, this is quite easy to see in the graph. We know that if f of x is equal to x, it is this line that looks like this. Okay, this is y is equal to x. It's called the identity function, which means that any x is the same exact y. So for example, if this is 3, this is 3. And then again, you can see here that if we look at the limit as it approaches from the left, and we look at the limit as it approaches from the right of 3, the y is still going to be the same as the x. It's going to be 3, right? Because the function is y is equal to x. The x's and the y's are the exact same for all the points on the graph. So the limit as x approaches c of x is equal to c. Now, for the next one here, the concept is kind of the same. And it tells you that if p is a polynomial, then the limit as x approaches c of p of x is actually just p of c. And that comes directly from properties of limits and the fact that you have these two very important limits here. Now, the reason that this is mostly true, and it comes from a concept that we'll talk about a little bit later, and it's a concept of continuity, right? And that is from the fact that from algebra classes, you know that a polynomial function is a nice, smooth, continuous curve, which means that the domain is all real numbers. So if I pick an x here, right, and this is my function p of x, I'm sorry, let me pick a c here, then this point on the graph would be c comma p of c. But I know because the function is nice and smooth and continuous that if I take the limit from the left and I take the limit from the right, it's just going to be the point on the graph. It's going to be this point, p of c. So if you know that your function is a polynomial, you can actually just plug in the c because the point will be the limit, which we have talked about in part one that is not always the case. But for a polynomial, it is the case that the point that what is approaching is actually the point itself, so you can plug in c. Now this works the exact same for a polynomial function, and remember that a rational function, and remember that a rational function is defined as a polynomial divided by another polynomial, and you can also do this as long as when you plug in the c, it doesn't make the bottom 0. Because remember that when c is, the bottom is 0, that fraction is undefined, right? So as a quick reminder, right, if you have a number that is not 0, right, over 0 yet, it's undefined. If you have a 0 over a number that's not 0, this is 0. And if you have 0 over 0, and this one confuses a lot of people, this is undefined. The bottom 0 always overpowers. Anytime you have 0 in the denominator, it is undefined. So that's important to kind of remember. Okay, so we can use this to find limits, and if you can plug in the C and it doesn't give you that the bottom is 0, then it's very quick to find the limit algebraically, right? So we have, find the limit as x approaches -1 of 3x cubed minus 4x plus 8. The first thing, and that might be kind of difficult for some people, is to recognize that this is a polynomial function. So because it's a polynomial function and the curve will be a nice smooth curve, then I can plug in -1 because the limit as it approaches -1 will be the actual point itself as shown in the diagram above. So I'm going to have 3 times -1 cubed minus 4 times -1 plus 8. And this is going to be 3 times -1 plus 4 plus 8, which is going to give me -3 plus 12 is equal to 9. And if you wanted to, you could use like a graphing tool on the internet and graph 3x cubed minus 4x plus 8 and also see this graphically if the graphing limits made sense to you, which hopefully it did. Okay, the next one is a rational function, again, because 3x cubed minus 8 is a polynomial on its own. X minus 2 is a polynomial on its own. So if you put them in a fraction, it's called a rational fraction. So if I don't get 0 in the bottom, which I won't when I plug in 1, I can just plug in the limit, the x equals 1. So 1 cubed minus 8 over 1 minus 2, oops. This is going to give me 3 minus 8 over -1. So this will give me -5 over -1, which will give me 5. So polynomial function, rational function. In the rational, as long as it doesn't give you 0 in the bottom, you can plug in. So we love when that happens. And again, if you want to see that function graphically, graph it in using an internet tool, and you'll be able to see the limit also approaching 5 visually. Now the question becomes, well, what happens when Q of C is 0? So there are a couple of tricks that we're going to work with, and the two main ones is either to factor or to multiply by the conjugate, and I'll do one of each. So first of all, we're going to find the limit of, as x approaches 1, of x squared minus 1 over x squared minus 3x plus 2. Okay, so the first thing you would want to try to do is to plug in 1. So we're going to have 1 squared minus 1 over 1 squared minus 3 times 1 plus 2. It's going to give me 0 at the top. 1 minus 3 plus 2. 1 plus 2 is 3, so it's going to give me 0 is 0. And I just told you, right, that this was undefined. But it doesn't mean that the limit doesn't exist, right? Because there could be a hole there. And we already talked about, right, that if there's a hole at the function, that the limit still exists, even though the point doesn't actually exist there. The limit exists because it's approaching there. So what I'm going to try to do is I'm going to try to factor, and if the bottom and the top have a common factor, there's a hole at the function there. So I'm going to have the limit, right? Still write the limit. You haven't taken the limit yet. X squared minus 1 factors very easily as a difference of squares. X minus 1 times x plus 1. And let's see if we can factor the bottom nicely. So this has to be x and this has to be x, and the only factors of 2 are 1 and 2. And to get a minus in the middle and a plus at the end, I need them both to be minuses. But as you can see here, this has a common factor, and this was actually the problem that was giving me a 0. So once I cancel them out, I have the limit as x approaches 1 of x plus 1 over x minus 2, and now you can plug in. So you have 1 plus 1 over 1 minus 2, which is going to give me 2 over -1 is -2. So obviously the diagram I have above is not a correct diagram because it would actually be at -2 that this is happening. But the concept is the same, that there's a hole there, but the limit as it approaches left and right still exists because it's the behavior as it's approaching and not the actual point. I know I keep repeating this, but it's important. Okay, the next one here is multiplying by the conjugate, and you want to do this, you want to try to do this if you see a radical. So again, the first thing we would do is we would try to plug in. So we would get the square root of 1 minus 1 over 1 minus 1. And I think everyone can easily see that that would be 0 over 0. So what we're going to do is we're going to take, again, I'm still writing the limit, and we're going to have the square root of x minus 1 over x minus 1. And I'm going to multiply by the conjugate, and if you've forgotten, right, a plus b, the conjugate of that is a minus b. So I'm going to multiply by the conjugate of the one with the radical, but what I do to the top of a fraction, I must do to the bottom, because really I'm just multiplying by 1. And I can multiply by 1 because it gives me the same thing I started with. So again, I'm still writing the limit. I haven't taken it yet. Always try to be organized in your work in mathematics. And then at the top I will FOIL. So the square root of x times the square root of x is x, minus the square root of x plus the square root of x minus 1. And at the bottom, I'm not going to FOIL out because you're going to see that, remember, we're trying to cancel something out. Now at the top, negative square root of x and positive square root of x cancel, and that always happens when you multiply by conjugates. The middle terms cancel, right? Because if you have a plus b times a minus b, this is a squared minus b squared. So here, I have that this is going to equal to the limit as x approaches 1 of x minus 1 over x minus 1 times the square root of x plus 1. And here the magic happens, right? The factors cancel. I love it. So this is going to give me the limit as x approaches 1. I have 1 at the top still of the square root of x plus 1. And now I can plug in. So I have 1 over the square root of 1 plus 1. 1 over 1 plus 1 is equal to 1/2. And there it is. The question now becomes, well, what if neither of those work? What if you can't factor? What if you can't multiply by the conjugate and you can't cancel the factors in the bottom? That makes it 0. And another third grade way is to make a table. So what we have here is, if you take a look, right, I take some x's. I took some x's from the left of 2, right? And then I took some x's from the right of 2. So the notation that we're used to here is that this would be the limit as x approaches 2 from the left, and this would be the limit as x approaches 2 from the right of our function, x plus 1 over x minus 2, x plus 1 over x minus 2. Now what's important to notice is if when we plug in 2, we would get 3 over 0, so this would be undefined. But again, that does not actually matter, as we talked about. It doesn't matter what it is actually at the point. It matters what happens as it's approaching 2. So what would happen here is you would start plugging in 1.9, 1.99, 1.99. And so I will do 1.9 with you, right? If we have 1.9 plus 1 over 1.9 minus 2, that would give us 2.9 over negative 0.1. And 0.1 is the same thing as 1/10. So dividing by 1/10 is the same thing as multiplying by 10, which would be negative 29. And then if you want, you can pause the videos and you can plug in the rest of them and see if you get it right. If you plugged in 1.99, you would get negative 299. And then the next one is going to give you negative 2,999. And then the last one is going to give you negative 29,999. And so I'm sure you can imagine what would happen if we added another 9 and so on and so on. All right, you would keep adding 9s. So what is happening here actually is that the y's are getting extremely small, and they are actually approaching negative infinity. So what happens is that the limit as x approaches 2 from the left of our function x plus 1 over x minus 2 is actually going to be negative infinity. Now what happens when we plug in the ones from the right? So if we do 2.1 first, it would be 2.1 plus 1 over 2.1 minus 2. This would give us 3.1 over 0.1, which again, right, it would give us dividing by 1/10, which is the same thing as multiplying by 10, so it would give us 31. And so again, if you'd like, you can pause the video and see if you can get the other one. So the next one would be 2.01 plus 1. And then you would be dividing by 2.01 minus 2, which would give us 0.01. And so that's going to give us 301. Oops. And then the next one's going to give us 3001. And then the next one's going to give us 30,001. So I'm sure then you can imagine the next one would be 300,001. And then it would be 3,000,001. So what's happening here is that the numbers are actually getting very big. They're not going to now down, they're going up. So here you have the limit as x approaches 2 from the right of x plus 1 over x minus 2 is positive infinity. So we have this, we have this. And as we know from before, if the limit from the left does not equal the limit from the right, the limit does not exist. So the limit as x approaches 2 of x plus 1 over x minus 2 does not exist. Now, what is happening here, right? So this is a rational function graph. And so in algebra classes, you learn how to graph rational functions graph. And so what happens if the factor in the bottom does not cancel, it means you have a vertical asymptote. So you don't have a hole, you have a vertical asymptote. So actually, oh, that was a horrible line. Let's try that again. Right, so actually you have a vertical asymptote at x is equal to 2. This rational function graph will also have a horizontal asymptote at y is equal to 1. And then the x-intercept would be -1. The y-intercept would be -1/2. And so your graph would actually look like this. And you can use, again, a tool if you want to see a nicer version. And on this side, it would look like this. And there you can see it, right? Let me make my point thicker. So as it's approaching 2 from the left, your graph is shooting down. So it's going to negative infinity. And as it's approaching from the right, it's shooting up. Now, at a vertical asymptote, this has to happen, one of the other or both. It has to either go to negative infinity or go to positive infinity. Okay, so if you know the behavior of asymptotes, this can also help you answer the question correctly. So as a quick summary here of what just happened in the introduction to limits, finding limits is looking at the behavior of the graph. The x-coordinate will be given to you and you are answering what the y-coordinate is doing. So you are looking at the behavior of as the graph is approaching the x, and you are finding what the y coordinates are approaching. So the key note here is the behavior, right? And then there are 3 main ways of finding a limit: graphically, algebraically, and by using a table. Happy finding limits.